The main idea of Lab 2 is to show the change of velocity of an object that is dropped from a still position due to the force of gravity, and this can be modeled by using Newton's second law. Newton's second law says that the final velocity vector is equal to the initial velocity vector plus the net force vector divided by the mass times the change in time. Now we know that the final velocity vector is not going to be equal to the initial velocity vector because the ball's velocity is not going to be equal to zero right before it hits the ground. So we can assume that there is a net force, mainly gravity, acting upon this ball as it approaches the ground. The net force vector is modeled by the weight force vector plus the drag force vector, where the weight force vector is equal to the opposite of the mass times gravity, which is 9.8 meters per second on Earth, times the j hat vector, which is equal to 0, 1, 0 in this case because we're only referring to the y component vector. And the drag force vector is equal to the opposite of proportionality constant times the velocity vector. Now, as the velocity vector increases, the drag force also increases, and the proportionality constant is there to give the correct position of the y value as it approaches the Earth. Now, when we go through tracker of a ball that I chose to use, we see that when it first starts out, the ball doesn't seem to move very much at all. It stays in a pretty similar position. It almost looks to be zero change. But as it approaches 0.6 seconds when the ball hits the ground, we see that the position changes greatly from one spot to another. It looks like that here it's almost a full frame or approximately 0.5 meters, and here it's almost 0 meters. And we model this through the velocity, the y component. We said it produces an almost linear slope where the magnitude of the velocity increases as you go through time. Now, when we model this through our tracker data, using the appropriate formulas, setting the mass of the ball correctly, and using the correct position and velocity vectors, changing the force of gravity to 9.8 meters per second, using the correct j hat vector, and making the net force vector equal to the weight force vector, and using Newton's second law to predict the final velocity and the final position of the ball. We run this through tracker, and we see the movement of the ball seems to represent exactly what we were shown through tracker, and each little individual point here on the curve produced by the VPython code seems to resemble exactly what we saw in the quadratic equation of the y component values that we saw through tracker. Now, when we look at this vector value, however, we see that the y component vector is not equal to the y component vector that we found during tracker. It should be negative 1.521, while here is negative 1.766. So obviously something is missing here. So we need to install the proportionality constant and the drag force in this situation. So you install the proportionality constant here after many attempts to find the correct value. We include the drag force, and we include the force into the net force value. And we also show the arrow scales to show the gravitational force and the drag force acting upon the ball. Now when we run this, we see that the gravitational arrow is always going to be the same, while the drag force arrow increases as the ball moves faster and faster as it approaches the ground. And when we look at the value produced through VPython, we see that this value is exactly equal to the value that we had during tracker. So this is a pretty good, if not identical, representation to what we had during our tracker. And when we view our handy-dandy little line graph, we do see that the model position with the drag that we just added is almost identical to the experiment position. We see that the blue dots of the experiment just line up almost identically with the model position of the drag. Now, the model position without the drag, which is what we showed the first time without the directional arrows, produces a line that is far below by 0.2 meters, the model position with the drag and the experiment position. This is because there is no net force besides gravity acting against the ball, and this is in a perfect vacuum kind of setting. Now, we know that because we're out in the world and there is air pressure, this is not a perfect vacuum setting, so there is an air force and a drag resistance against the experiment. Now, if we were to possibly maybe throw the ball down instead of just dropping it from still position, we would model it by using this. The velocity equation is equal to the final position minus the position before it, divided by the final time position minus the time position before that. So the velocity from the initial position, when we dropped it, was found to be negative 4.69 meters per second right before it hit the ground. Now, this should be negative right here, not positive. There we go. The velocity, if you use the initial velocity is equal to this value instead, we would see that the final velocity is going to be equal to negative 5.0 0.95 meters per second. So if we were to throw the ball initially to the ground instead of just dropping it from a still position, the velocity at the bottom right before it hit the ground would be faster, and this does match up scientifically correct. But, however, the drag force is going to be stronger on this because the ball is moving faster before. So, even though the ball does move faster in this situation, it will have a stronger drag force acting against the ball right before it hits the ground. We can show this to be true by running VPython one more time and changing the initial velocity vector instead of being to 0, 0, 0 to 0, negative 2. The ball is initially moving at a speed of negative 2 meters per second as soon as it starts running the tracker. Now, when we model this, we see the ball is moving initially when it starts, and that the drag force at the end is larger than the drag force at the end when we initially just drop the ball from a still position. And when we look at our y component value, we see that it's negative 2.478 instead of being at negative 1.521. So it is almost 1 meter lower than what it would have been when we just dropped the ball from a still position.